Welcome everybody to 7.3. Today we're going to talk about probability and finding the probability of compound events. For our learning target today, we have I can describe how to find the probabilities of compound events. Compound events means like two or more events. So before, when we just started looking at probabilities, we were just looking at like the probability of rolling a die and what are the odds of getting a 6? Well, it's 1 in 6 chances. Now, for compound events, we would say things like rolling a 6 and flipping a tails. So we're taking two events and we're seeing how that affects our probability. Or more, two or more. All right, starting with a little bit of vocab, the set of all possible outcomes of one or more events is called the sample space. So all possible outcomes. You can use tables and tree diagrams to find the sample space of two or more events. Okay, so that's what we're going to do in the first example here is to find a sample space. You randomly choose a bread and type of sandwich. Find the sample space. How many different sandwiches are possible? Okay, so we're making a sandwich here. We've got two different types of bread we can choose from, and we've got 4 different types of meat that we can choose from to make a sandwich. And we want to know how many possible outcomes are there, or in other words, what is the sample space? So I'm actually going to use a tree diagram to start here and kind of show you how that models all the different types of possibilities. Okay, so the first thing I'm going to start with is my bread selections, and then I'm going to my type of meat, and then what's my outcome from that. Okay, I might use some abbreviating here just so I can fit everything. So, well, I could have wheat bread, and on my wheat bread, I could have ham, I could have turkey, I could have steak, or I could have chicken. So I have wheat bread with ham, I have wheat bread with turkey, I have wheat bread with steak, and I have wheat bread with chicken. So there are 4 outcomes. Now I could also have sourdough bread. So I could have sourdough bread, and I could have that with ham, I could have that with turkey, I could have that with steak, or I could have that with chicken. Okay, so then that would give me another 4 outcomes. I could have sourdough with ham, I could have sourdough with turkey, I could have sourdough with steak, or sourdough with chicken. Okay, so this is what they consider a tree diagram right here, and it kind of just helps us show all the different outcomes or possibilities for the different types of sandwiches. So we have 4 sandwiches that with 4 different types of meat with wheat bread and 4 more with sourdough bread for a total of 8 different sandwiches possible. Okay, why don't you go ahead and pause the video now and try the try it problem. All right, the try it says, what if the sandwich shop adds a multi-grain bread? Find the sample space and how many sandwiches are possible now. Okay, now we would just add another bread category. So now we add in an M for multi-grain, and then we still have all the different meat options. So ham, turkey, steak, and chicken. Okay, so we add 4 more to our total of 8. So how many sandwiches are possible? Well, 12 different sandwiches are now possible. Okay. All right, a little more vocab here. It says you can use the sample space or the fundamental counting principle to find the total number of possible outcomes of two or more events. So, in other words, what we're going to learn about the fundamental counting principle is the same as this. It's just another way to do it. Okay, and I'll show that to you here. It says the fundamental counting principle can be extended to more than two events. An event M has M possible outcomes. An event N has N possible outcomes. The total number of outcomes is M times N. So let's take this previous example here. Let's say one event was bread and one event was the type of meat. And I wanted to know how many possible outcomes. Well, there were 2 choices for bread and there were 4 choices for types of meat. So what's 2 times 4? Well, 8. So same goes here. If for the try it problem, if we added a type of bread, this would now be 3 types of bread. And what's 3 times 4? Well, 12. Same answer we got here. So I do think that the tree diagrams are very beneficial and very helpful to be able to see visually that all of your data displayed, but realize that there's also this fundamental counting principle that we can also use to our advantage. So let's try the fundamental counting principle in example 2. It wants us to find the total number of possible outcomes. So similar to what we just did. And it says, find the total number of possible outcomes of rolling a number cube and flipping a coin. Okay. Now, I want to show you, we could make a table to represent this, right? So let's just do that quick. We could roll a 1, we could roll a 2, we could roll a 3, 4, a 5, or a 6. And what else? Well, we're also flipping a coin. So we could flip a heads or a tails. Okay, if I make a table here to kind of represent that. So I could roll a 1 and flip a heads. So that would be 1 each. I could roll a 2 and flip a heads. I could roll a 3 and flip a heads. I could roll a 4 and flip a heads. You kind of get the idea here. And the same goes for tails. I could roll a 1 and flip a tails. Roll a 2 and flip a tails. So on and so forth. How many different possibilities do you see here? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different possible outcomes. Could we get the same answer using this fundamental counting principle? Well, absolutely. How many sides are on a dice? 6 possible outcomes there. And how many sides are on this coin? 2. And what's 6 times 2? Well, that's 12. So there are 12 possible outcomes. Sometimes, though, it can be helpful to see it in a table. So again, either method will work. Go ahead and pause the video now for the try it. Okay, for the try it, it says find the total number of possible outcomes of spinning the spinner. So I've got 1, 2, 3, 4 different possible outcomes there, times randomly choosing a number 1 to 5. Well, there's 5 letters there, or 5 numbers, so 4 times 5 would be 20 possible outcomes for the try it problem there. Alrighty, let's move on. If you have questions on that, please let me know. In example 3, essentially we just add another event. Finding the total number of possible outcomes again. So same thing we've been doing before, but now we're not just talking about 2 events. We're saying how many outfits can you make from the t-shirt, jeans, and shoes in the closet. Okay, so now we have 3 events. So let's say event 1 is t-shirts. How many t-shirts do I have to choose from? 1, 2, 3, 4, 5, 6, 7. 7 different t-shirts to choose from. Event 2, I have jeans. How many different jeans do I have to choose from? Looks like 1, 2, 3, 4 different pairs of jeans. And lastly, how many different, event number 3, I also have shoes. How many different combinations of shoes? Well, I can wear this pair, 1, 2, or this pair, 3. So I have 3 pairs of shoes. So just like before, I'll use the fundamental counting principle. 7 times 4 is 28. 28 times 3 would give me, let's see, 84. So 84 different outfits. Now you can kind of start to see that if you were to make a table for this, 84 different slots in the table would kind of take up a lot of space, and it might be tricky to do. Again, you could do a tree diagram too, but that's a lot of different outcomes. So sometimes it's a little bit quicker to use the fundamental counting principle. All right, on to the definition of a compound event. That's when we have 2 or more events. As with a single event, the probability is the quotient of the number of favorable outcomes and the number of possible outcomes. So we're still doing number of favorable over the number of possible. Same as before, but it'll change a little bit because now we have 2 or more events, not just 1 event. So example 4, where we find the probability of a compound event, says, in example 2, what is the probability of rolling a number greater than 4 and flipping tails? Okay, so what I like to do is I like to think, okay, what is the probability of my first event? So the first event, rolling a number greater than 4. Well, what are numbers greater than 4 on a number dice? Well, that's either 5 or 6. So I have 2 favorable outcomes over how many total sides on the dice? Well, that's 6 sides. Right? So that's 2 out of 6. So my first event, the probability that I'll roll a number greater than 4 is 2 out of 6, or 1 out of 3, same thing. I need to multiply that by my second event. And my second event is flipping tails. Well, what's the probability of flipping tails? Well, that's pretty easy. It's 1 favorable outcome out of 2 possibilities. You could either get heads or tails. So all I need to do is I need to multiply 2 6 times 1/2. I'm multiplying my 2 events together. So 2 6 times 1/2. 2 times 1 is 2. 6 times 2 is 12. And 2 twelfths simplifies down to 1/6. So the probability is 1 out of 6. Not very good. It's definitely not impossible, but it's unlikely. That would give me, I think it's that 16 2/3 or 16.66% chance. Okay. Go ahead and pause now for the try it. All right. It says in example 2, what is the probability of rolling at most 4 and flipping heads? So what does at most 4 mean compared to the other problem of where it said a number greater than 4? you got to kind of think about that, and then also flipping heads. So probability of rolling at most 4. So could you roll that? That would kind of be like the opposite. So you can't roll a 5 or a 6. So you can roll a 1, a 2, a 3, or a 4, right? And then, so what's the probability of that? Well, there's 4 possible or favorable outcomes over a total of 6 possible when you roll a 6, when you roll a cube, a number cube. So 4 out of 6 is the same as 2/3 for our first event. And we need to multiply that by our second event. So flipping heads, same as 1 out of 2. So when we do that, 2 times 1 is 2, 3 times 2 is 6, so 2 out of 6 is the same as 1/3, or 33% chance. All right. Last example here, for example 5, it says, on a game show, you choose one box from each pair of boxes shown. In each pair, one box contains a prize and the other does not. What is the probability of winning at least one prize? Okay, let's use a tree diagram to kind of break this down. All right, so I'm going to use the same colors here. You might want to do it a little bit differently in your paper, but I just want to show that. So in each pair, one box contains a prize. So I'm going to say for the red, my first choice, I'm going to say one of them contains a prize and one of them does not contain a prize. So that's prize and no prize is what those stands for. Okay. Now, again, you have another choice, choice 2. Well, you could choose the one with a prize or the box with no prize. Okay, so we could say the same for this choice. Maybe in choice 1, you pick the box with no prize, but you still have a chance in choice 2. So you could pick the prize box or the no prize box here. And the same goes for your third choice, right? So for each one of these, you could say prize or no prize. Prize or no prize. The idea kind of continues on there. You kind of probably see the pattern. Okay. Now, what are my outcomes? Well, I could get really lucky and I could choose a prize in each one of these. So I could choose a prize on my first choice, a prize on my second choice, a prize on my third choice. 1, 2, 3. That would be pretty amazing. Or I could choose a prize on my first one, a prize on my second one, and no prize on my third choice. You can kind of see the pattern here. So I could choose a prize, not a prize, and a prize. Or I could choose a prize, not a prize, and not a prize. I'm going to keep going with this. So there is my first half, right, where I choose or I got a prize in my first box. Well, maybe I don't get a prize in my first box. I get a prize in my second box and a prize in my third. Or I could do NPN or NNP or NN, and not a prize in all of them. I could get really unlucky. Now the question says, what is the probability of winning at least one prize? Well, let's look. Did I win a prize here? Yep. Did I win a prize here? Yep. All I need is to have one prize is what it asks. One prize here and 2 no prizes, but I still got at least one, right? At least one, at least one, at least one. There's only one situation in which I don't get a prize. Okay. So how many is that? 1, 2, 3, 4, 5, 6, 7. So I have a 7 out of a total of 8 chances. Is my probability of at least one prize. Okay. Number of favorable outcomes. Well, there's 7 over the total outcomes. There's 8. So 7 out of 8 is what? 7 divided by 8 is 87.5%. pretty good chance of getting at least one prize. Let me know if you have questions on that one. Hopefully that modeling kind of made sense to you and help visualize that. That does it for compound events in section 3. Thanks for watching. I'll see you guys next time.